So a lot of things that we use in these days uh, involve graph theory. Everyone has a smartphone, right? Or everyone, well, I'm assuming everyone has the internet here because, you know, how else would you supposed to be a Compton Club? Um, but assuming everyone here has the internet, has used something like Google Maps, and let's say we wanted to get somewhere. How would you determine how to where how where to go, where to go, how to get to some destination? And that's the kind of my joke of my of this week's lesson is how do I get home? All right. So that's what graph theory is kind of is. It just it relates to graph. It's the theory of graphs. So in previous lessons, I've just been covering fundamentals of Python as well as introducing some key concepts relating to studying algorithms. So I covered efficiency, uh, and that gets you started with learning about algorithms. However, we haven't really covered any algorithms or category of algorithms. But today we'll be covering one of these categories, and it's called graph theory. So we won't be coding too much today, but we'll be covering the basic concepts so that we can prepare for next week, where I'll be showing you guys some graph theory applications. All right. So introduction to what graph theory is. So to get started with graph theory, you need to define what a graph is, as the name applies. And because since graph theory involves graphs. So formally speaking, a graph is a set of objects with some sort of relationship. But generally speaking, this consists of vertices and edges consisting of a pair of vertices. So looking at this, like we can picture this as like the vertices as a bunch of locations on the map. So and the edges being roads connecting these locations to other locations. But we can also go one step further and actually visualize this graph with the vertices as points and circles and edges as lines connecting them together. So vertices are also numbers so that you can distinguish between them. So let's say, Massey is one location. We want to go to, downtown Windsor as another location. Another location is the mall. Another location, let's say, is all the way at Union Station in downtown Toronto. All right, we can draw a road we can let's say I visualize this. All right, let's say we have like a bunch of circles. So like this is the one. Let's say that represents Massey. Connects to downtown, which is number two. Connects to the mall, number three, and then let's say there's a direct road to Toronto from the mall, and that's four. And we can visualize a graph like this. So like you can imagine like these are just a bunch of like a bunch of locations, and then like there's only like these roads that you can travel on. All right. So that's how we can visualize a graph. Now sometimes we can place restrictions or add features to a graph. And an example is like let's say like some roads we think about they're one-way roads, so you can only travel in one direction. This is what we call a directed graph, in which you're only allowed to travel in a certain direction on an edge. Either you can travel in one direction, or sometimes the graph allows you to travel in both directions if there's roads connecting both directions. And this is in contrast to an undirected graph, in which you can travel in both directions on on an edge. It doesn't matter. Like let's say like here, right here up top, it's an undirected graph since it doesn't specify what direction I can travel in. So we just assume, hey, you can travel in both directions. So I can go from 5 to 4 or 4 to 5 on this road. Now, but rather than calling these edges, we call them arcs. So more terms we use with arcs is that there's an out degree of a vertex, which is the number of arcs that begin at a given vertex, and an in degree of a vertex, which is the number of arcs that end at a given vertex. So let's say, we have like, there's only two roads that go to 4, all right, in a directed graph. We'd say there are two, that there are two in degree arcs of that are connected to 4. And I'll say there's only one one road that leaves the fourth vertex. All right. Now you'd say there's one out degree arc. All right. And another restriction slash feature of a graph you can add is adding weights to a graph. So this is what we call an edge-weighted graph or a weighted graph, where each of the edges of the graph has an associated weight or cost to them. So you guys know what a toll road is, right? So it's like a road that you have to pay money to use. And a common example is the bridge, the Ambassador Bridge to Detroit. You have to pay money to actually go on that bridge. So there's an associated cost with it. Or with the tunnel. The tunnel, you have to pay a certain amount of money to it. So rather than thinking of it just exclusive for like where you have to pay a certain cost to use that road. Or if you go to Toronto, does anyone know what the 407 highway is? Um, for you guys who don't know what the 407 highway is, it's essentially a toll. It is a toll road. So in order to use that specific highway, you have to pay a cost to it. And it's not just like the tunnel or the bridge where the tunnel and the bridge there's only one you get on, you get off. With the 407, you pay by a certain distance. So wherever you get on, where you get off, there's an associated cost with it. So you can think of them as toll roads where you have to pay a certain price to use a road, and instead of just being exclusive for a single road, it applies to all roads. So like every single road has a cost to it. So like let's say in Windsor, if I want to drive, there's a cost there's a toll road on every single road. Complete mayhem, like chaotic scenario. But just imagine that. So since every single road has an associated cost, I have to, think about it. Hey, I want to maximize. I don't want to spend too much money. So I have to like think what roads do I not want to travel on so I can save money. All right. We'll cover a bit of that later. But yeah. Um, and then there's also like sometimes you don't want to think of them as costs. Let's say you want to get to some location the fastest. All right, like you don't want to be stuck in traffic, or like just stuck in like low speed zones, low speed roads. And so rather than sometimes thinking of the cost, like sometimes like you can think of it like, hey, which roads are the fastest? So like you can have like each edge having a weight associated with them, and the weight is associated as like the speed of the road. And let's say I want to take the fastest road. I want to get to let's say I'm running late to school. I want to get to Massey as quick as can as possible. So I can just look at the weight of the road and just be like, okay, this is how fast I can get to Massey. All right. So that's what the weight is. So here's a combination of both graphs, so an edge-weighted directed graph. So you can see here on the edge-weighted directed graph, there's a weight to each road. So this road from 0 to 5 has a weight of 2. So it costs me 2 units or whatever to take this road. Or it gives me 2 units, it just depends. And you could see with this directed graph, there are arrows pointing where I can go. So from 0, I can only go to 0. I can go to 4 or 5 or 2. From 2, I can go to 3, 4, or 0. From 1, I can only go to 5 or 4. From 5, I can't go nowhere because there are no roads that lead from 5. So there are 0 out degree arcs from 5. So this is how it looks like to visualize an edge-weighted directed graph. Does anyone have questions about what I just talked about just now? No questions? All right, I'll carry on. Okay, so in regards to how we can write this graph on paper, we can draw the vertices and edges in a set we can write down the vertices and edges in a set, and then the edges as a pair of two values. So we denote the vertices as v and the set of edges as e. So for directed graphs, the starting point is usually the first value in the pair, and the second value is the ending point, showing the direction. And for weighted graphs, you'd add an additional value to denote the weight of the edge. So this first graph here, so there's 6 vertices in total. So you have v equals 0, 1, 2, 3, 4, 5. And the edges be, so there's an edge from 1 to 5, or 5 to 1, since this is undirected, 0 to 5, 5 to 4, 4 to 1, 0 to 4, 2 to 0, 4 to 2, and 2 to 3. Alright? For a second graph, it would be 0, 1, 2, 3, 4, 5 for the vertices, since they're the same number of vertices. But for edges, there's a arc from 1 to 5 with a weight of 6, 1 to 4 with a weight of 5, 4 to 5 with a weight of 9, 0 to 4 with a weight of 1, so on and so forth. So that's how you could write down the this graph, I guess. And you can take this information and you can draw a graph from it. So beyond just looking at the edges, we can look at paths, which is just a sequence of vertices that there exists edges that connect between each vertex. So we can write it like this. So it's like this v0, so where you started at, all the way to vk, where you're ending at. All right, and there must exist edges from v to 0 to v to 1, v to 1 to v to 2, so on and so forth, until you reach v to k minus 1 to v to k. And the length of this such path is k. So going back to the first graph, there exists a path 5, 4, 2, 3. Since, let's say we start at 5, we can go to 4, we can go to 2 to get to 3. So you can use this path here to get to 3. And, there are, k edges. So we start at 0, right? So we start at 0, 1, 2, 3. There are 3 edges that connect from 5 to 3. The path is said to contain vertices. The vertices v to 0, v to 1, all the way to vk, as well as the edges v to 0, v to 1, all the way to v to k minus 1 to v to k. Since, along this path, we stop by these vertices. So it contains these vertices, so 5, 4, 2, and 3. And also has the edges as well, since that's the only path, that's the path you can take. So 5 to 2, 5 to 4, 4 to 2, and 2 to 3. And a vertex is said to be reachable from another vertex if there exists a path between the two. So sometimes, there aren't, it's not possible to reach a vertex. So let's say from 5, in this directed graph, it is not possible to it's not possible to reach any of the other vertexes, since there's no edge that leads from it. So we can just say all the other vertices are unreachable. All right. So, and a path is simple if it contains no vertex more than once. So, sometimes, let's say we have 5, 4, 0, 5, 1. That is not simple. It wasn't simple, but 5, 4, 2, 3 was simple. All right. And a path is a cycle if it starts and ends at the same vertex. All right. So if we have here 5, we start at 5, we go to 4, we go to 0, and we go back to 5. That's a cycle, since you start and you end at the same position. Now a cycle can still be a simple path, so long as the only thing that repeats in that path is the beginning and the end. That's it. There are no other repeats. So let's say we have 5, 4, 3, 5, 4, 3, 5, 5, 4, 3, 5, 4, 3, 5. Once again, that is not simple, since you're repeating 5 once again. It's in the middle. You're also repeating 4, and you're repeating 3. All right. Diving a bit deeper into graph theory, you can say more descriptive things about the graph using terms. So here are some terms you can use. So a self loop. So a self loop is an edge that starts and ends at the same vertex. So I couldn't really easily visualize this, but let me just visualize it here. So let's say there's a road starting at 1. It starts at 1, and then goes back to 1. In order to visualize this, you can just like you just draw like a line that loops back on itself. So yeah, so that's how you draw a self loop. A simple, it's a name of a graph, a simple graph. So not a simple path, a graph is a name of a graph that contains no self loops or repeated edges. So sometimes you can have multiple edges like this. But a simple graph is a graph that has no loop, self loops, or repeated edges. All right. A multigraph is a name of a graph that does contain at least one self loop or repeated edge. So it's a dichotomy, I guess. So you can have a self loop, or you can have a simple graph, or you can have a multigraph. Either or. Incident is the vertices that are connected with an edge. So let's say we have this edge here, right? 1 and 3. This edge here, so this edge 1, 3, is incident to the vertices 1 and 3. All right. Degree is the number of edges that are incident to it. So the degree of, let's say, 1 here is 2. Since there are 2 edges that are incident to 1, we'd say 1, the vertex 1 has the degree 2. Here with 3, in this case, there are 4 edges. There are 4 edges incident to 3. So that means it has a it has degree of 4. I forgot this extra graph line here. Edge here. It has a degree of 4. Adjacent. So adjacent is the number given to a vertex if it's incident to another vertex. So it's kind of like what's next to each other. So like here, 1 is connected to 2 and 3 through these edges. So 1 is adjacent to 2 and 3. 3 is adjacent to 2, 1, and 4. So that's the name given to a vertex if it's incident to another vertex. Sparse is a number given to a graph. The total number of edges is small compared to the total number possible. So the total number of possible edges is n times n to the minus n to n times n minus 1 over 2. The reason why is because there's you have, let's say we have like a graph like this, like you can have a graph. So let's say we have here with this graph here, like it can branch off into like 3 possible locations. 2 can branch off into if we already covered this one, then it can only branch off into 2 more, and so on and so forth. Simply, it could just be another way of saying it is n choose 2. But simply speaking, it's n times n minus 1 over 2. Since I don't want to confuse you guys with choosing and such. All right, and then that's the name given to a graph if the number of edges is small, and it's kind of all relative. So it depends whether it's sparse or dense. And dense is the name given to a graph if the number of edges is close to the total number possible. Yeah, it's all relative. So but we won't be using it too much since it's all relative, I guess. Moving on. Does anyone have questions about what like this whole introduction, I guess?
I'm sorry, so I was a little bit late. Like so do you mind just like briefly summarizing like just briefly summarizing like what a graph is, like why like the numbers are sort of like not chronological, just random, I guess.
Oh, so
Yeah.
it
Yeah.
it's kind of random, and it's not. It's random in the sense that like how do we kind of want to best visualize it. Like it's random in the sense that like we don't want like 0 So like say here, if we had it in order, like we'd have 0, 1, and such, we'd kind of have to be looping around whatever the numbers are, because 0 and 1, 0 is only connected to 2 and 2, 4, and 5. So like we'd have to be like doing some like crossing over loops and paths and such. The way it's visualized is we're trying to make it as clean as possible. So you can visualize it like this if you want to. Um, but most people I know, I personally want a clean graph because it's easier to work with. So that's why it's not necessarily random. It's just like how do we make it look as clean as possible? So does that answer your question?
Yeah.
All right. So connectedness and other graphs. So in a given undirected graph, it is said to be connected if there is a path from every vertex to every other vertex. So the graph that I showed in the first graph, I showed in the first lesson here, is completely connected. Since there is a possible path from one vertex to another, you can kind of clearly see everything is kind of connected to each other. So like I can get to 5 from 3. I can get to 5, or 5 to get 3, 0. I can get to anywhere, starting from anywhere. All right. So while the following graph I will show you is not connected, so that you kind of see like I can't get to 3 from 5. Like this is completely isolated from each other. You can kind of see like it's like something's it's not possible to get somewhere, you know. All right. And a component of a graph is a maximal subset of vertices, such that for every vertex is reachable from each other vertex in the component. So this graph above has two components, 0, 1, 4, 5, and 2, 3. So it's like, if I split this graph, this graph is kind of just split into two separate graphs, I guess. And you can have like this component here or this component here, you know? It's like two separate graphs, I guess. A direct graph, a directed graph is said to be strongly connected if there is a path from every vertex to every other vertex. All right. So, you know, with directed graphs, there is a way it is possible for to not be able to reach some value other vertex, and you can see here, 5 is not reachable. It cannot reach any other vertex, and it is said to be strongly connected if it's possible to start and end anywhere on the graph. And a strongly connected component of a directed graph is a component where a given vertex has a path to all other vertices, and all of those vertices have a path back to the given vertex. So a directed graph doesn't have to be strongly connected, but it can have strongly connected components. So like a given vertex can start and end at the same place. So everywhere in the component, so the component is like how we can split up the graph. It can start and this graph, it can start and end anywhere. All right. Now a subgraph is a graph that consists of some vertices and edges of a larger graph. All right. So let's say we have this is usually denoted as like G with an apostrophe equals like V apostrophe and E apostrophe, where the subgraph is denoted as G. And the much larger graph is denoted as G equals V and E, and V apostrophe is being a subset of V, and E apostrophe is being a subset of E. So a subset is so you have this main large set itself of V and E. So let's say we have this large set. A subset is something contained within it. It only contains some values or something. It can contain all the values. That is a valid subset. But generally, when we think of subsets, we think of something. It contains only a portion of what the much larger set contains. So a subgraph only contains some of the edges and some of the vertices. of a much larger graph. And an induced subgraph is a graph G where the subgraph G where all those edges in the subgraph consist only of edges that have points between vertices and V apostrophe. So we look like the original graph, and an induced graph of V apostrophe 0, 1, 2, 3 would look like something like this. All right? Since, so if we go back to the original graph, so let me just copy and paste. Let me just copy and paste it so that we can kind of see. Copy. If I doesn't seem to let me paste, but let me try doing this. All right. Okay, so we have the vertices 0, 1, 2, and 3. So we have 1. Let me just change the color as well. We choose a different color. So we have 0 here, 1, 2, and 3. All right. So 0, 2, and 3, they all have edges to each other, right? And 1 is just off of nowhere. And we want to get all the edges of this much larger graph in such a way that it only consists of edges between each other. So 1 is off of nowhere. 1 has no edges connected to any of the other graphs, other vertices, while 0, 2, and 3 are connected. If we include 4 here, if we have an induced subgraph of 4, then we can include 4 here, and then it looks something like this, right? So those are what induced subgraphs are. Beyond those types of graphs, there are special types of graphs that we can cover. We need to cover. So a tree is an undirected graph that consists of no cycles and is connected, right? So many trees are what is called rooted. So where there is a notion of some top node, which is usually like some root, right? You can kind of imagine like a tree, Think of it like an upside down tree, actually. You know how like a tree, if you draw a tree, like it branches off into like multiple different branches, right? Like it goes off like into branches and such. And it starts with some number, and it branches off into smaller numbers, right? You can kind of imagine a tree as an upside down physical tree. So a tree in graph theory is like an upside down real life tree. And it has a notion of this top node, which is this root. So you can kind of like imagine like the root of like a tree, like the trunk. It's like this one number, I guess. And each node has a parent, which is adjacent nodes closer to the root, and nodes has children, which are adjacent nodes further from the root. And nodes have siblings where they're on the same level or like same level, but which means they have the same distance from the root. So let me clarify, like visualize this. So this is the root of the tree, right? So this is the very top. We have this notion that this is the root. This is the top of the tree, right? Now looking at 7 here, the parent, so what number comes before it? What number is closest to the root is 2. Or like we look at this number here, 2. Its parent is 7. Like we can kind of like imagine like a family tree as well. What's your parent? What's above you, I guess. And then it has children. So like 7 has children 2 and 6. All right. And we can look at things of the same level. So like 7 and 5, we would consider these children. Because they're on the same level. They're the same distance from they're not children. They're siblings. They're the same distance from the root, I guess. One neat thing about a tree is that you can hold it from any node, and it should create a tree. So let's say we recreate this tree, right? And starting from 4, and we make 4 the root. We can visualize this now. We have 4. Why is it not changing? 4 goes to 9, goes to 5, goes to 2, goes to 7, which goes to 2 and 6, and 6 goes to 5 and 11. And this is a completely valid tree. You can hold it from 9, and this 4 will just swing down over and look like something like this. And you can hold the tree in any way. You can have the root of any number of any node on the tree, and it's a completely valid tree. That's what a tree is. All right. So an undirected graph that contains no cycles but isn't connected is called a forest. So let's say we have like, we 5 and 9, they're no longer connected. All right, and we have like 9 and 4 off over here. This is what we call a forest. So it's, we can imagine it like it's multiple trees. So we call this a forest, since it's not connected. So you can't go from 11 to 9 here. It's not possible. So this here would be a forest instead, since it's like this would be a tree, this would be a tree. Think about it, multiple trees, that gives you a forest. So, and directed acrylic, it should be, wait, did they do something wrong? It should be directed that, it should look like that. A directed acyclic graph is simplified as DAG. So it's a directed graph with no cycles. So you can't start and end the same place. So let's go back to this graph up top. Let's see if there's a cycle here. So you can start from 0 and you can go back to 0. This is a cycle graph. If there wasn't a cycle here, so like let's say we flipped, there was no edge here. Or like, let's say this would also make it a cycle as well. There's a cycle. There are cycles here. A directed acyclic, graph is a directed graph with no cycles, and it's simplified as DAG. All right. A graph is said to be complete if there's an edge between every pair of vertices. So a complete graph is dense, as a dense graph, and there's an edge between every single vertex on the whole graph. All right. And a graph is said to be a bipartite if the vertices can be split into two sets V1 and V2 such that there are no edges between the vertices of V1 or the vertices of V2. All right. So there are no vertices between U and V. No, between it like the sets themselves, but there are edges between vertices in U and V. All right. So is that clear to everyone? Does anyone have questions about that? Guessing no one has questions. All right. So finally we coding this graph out, I guess, representing this graph. There are multiple ways of representing a graph like this, and it all depends on the question, as certain representations use different time and space complexities and things like that. So in terms of vertices, they are generally tracked by numbering them from 0 to n so that we can index them by their number. So instead we'll be focusing on the edges. Keeping track of the vertices is perfectly fine. There are multiple ways. So I'll be going through each of them. There's edge list, adjacency matrix, and adjacency list. So edge list, this is the simplest approach of keeping track of edges. It's just keeping track of the pairs of vertices on the graph. We were doing that earlier. We were just keeping track of the edges between each of the vertices, and that's about it. So you just get a pair of numbers and just throw them into a list and just keep track of the edges. Overall, this representation is simple to code. You just ask the user, hey, what are the edges? You know, tell me how many edges there are, and loop through. Okay, give me 2 values, and this edge is now starting from this vertex and going to this vertex. All right, and that's what an edge list is. You just take these values, just throw it to a list. I'm done. Relatively space efficient. It's really easy to add edges to an edge list. You just take this value, plop it into the list, and you're done. Deleting edges, on the other hand, as you don't know where you're not keeping track of the edges or whatever. You're just throwing them into the list, and you're just like, okay, have fun. In determining which edges are incident to a given vertex, it's time consuming. You have to loop through the whole list and be like, okay, which vertex corresponds to what? What is where do I go and things like that. So, and suppose determining which 2 vertices are adjacent, you have to go through and check. Okay, does this vertex is there a vertex? Is my vertex incident to a given edge? And give me all the edges, all the vertices that are adjacent to. Give me the vertex that's adjacent to this vertex on this edge. Really complicated. For weighted graphs, this representation is also simple. All you just need to do is just add one more value for each edge in the list. So an example of an edge list for an undirected one-weighted graph is something like this. So you have you're storing 2 values, the start of the one vertex and another vertex, and just keeping track of the edges. So this edge here goes from 4 to 3. This edge here goes 1 to 3. This edge here goes to 2 to 5, 6 to 1, 3 to 6. Simple. Another method of representing a graph is an adjacency matrix. So this is just an n by n array. So n is the number of vertices that contains a value at I and j. And it depends on the type of graph it is. So what are the values just completely depend. So the graph is unweighted. The value typically just denotes the number of edges between vertices I and j. If there are no multiple edges, I guess you can just keep track whether or not it is connected or not. Simple. If the graph is weighted, the value typically denotes the weight of the edge. Typically. For an undirected graph, this matrix is this symmetric, since if there's an edge between I and j, there must also be a edge between j and I. Simple. And overall, this representation is also easy to code. However, it is a bit less space efficient since, the space complexity is O at n squared. You're storing an n by n array, n squared. Debugging is a bit harder as you get this massive matrix, you have to go through this massive list, 2D list or whatever, finding certain values or something. Finding all edges incident to a given vertex is fairly expensive since, it's linear in the number of vertices. You have to go through, okay, starting at I, whatever, tell me what whether or not I'm incident or not. It's pretty, it's fairly expensive. But, checking if 2 vertices are adjacent is pretty quick though. You just do is just like, hey, is there a number at I and j? Is there? If there is, okay, I'm connected. And adding and removing edges is also fairly inexpensive. So all you have to do is like, okay, at I and j, just change the value. That's about it. Or at j and I, just change the value. So an example of an adjacency matrix for a weighted directed graph is something like this. So here, vertex 2. So let's say this column here, this here is a starting graph. This is where you start. This is where you end. So you can start from 1. So there's only one edge that leads from 1, and that goes to v2 with value 6. From v2, there's one edge one arc that goes to 1 with a weight of 1, and to 3 with a weight of 3. From 3, there is one arc that goes to 1 with a weight of 2, and goes to 4 with a weight of 2, and from 4 there's a arc that goes to 1 with a weight of 3, and to 3 with a weight of 2. Alright, and that's what adjacency matrix is. Lastly, is a third representation is well, one more representation is a graph is to keep track of all the edges incident to a given vertex. This is usually done by creating an array of length n, and then the ith entry in the array is a list that consists of the edges incident to the ith vertex. So let's say, we would just want to know what edges are connected to, this this vertex here, and that's what an adjacency list is. It just keeps track of what edges are adjacent, what vertices are adjacent to a given vertex, and a weight associated with them if it's a weighted graph. And this representation is also a bit more difficult to code, especially if the number of edges incident to each vertex is not bounded. So you can just have, if you have an infinite, some really large number of edges, it can get out of hand pretty quickly. Debugging this is also difficult. However, this representation uses a similar amount of memory as edgeless, since you're just keeping track of the edges pretty much. Finding the vertices adjacent to each node is pretty cheap, since you just have to loop through like this list and this the values inside this given value, I guess. But checking if two vertices are adjacent requires checking all the edges adjacent to one of the matrix. So that's it depends on how many edges are connected to a given vertex. And adding an edge is easy, but deleting an edge is difficult since you don't entirely know the location of the edge in the list. It's similar to an edge list where you just don't know where the edge is. And to accommodate for weighted graphs, rather than each list consisting of the vertices adjacent to the ith entry, it consists of a pair of values. So that have both the vertex adjacent to the ith entry and the respective weight to that vertex. And directed graphs are easily handled on this structure, as you can only keep track of one edge that starts from a vertex, or keep a separate list of incoming and outgoing arcs, or denote the direction of each arc in the list. All right, and here's an example of an adjacency list for a weighted directed graph. All right, so from 1 here, you can go to 3 with a weight of 2, or 4 with a weight of 6. From 2, you can go to 3 with a weight of 1, or 1 with a weight of 2. So you can go from 3 to 6 with a weight of 2, or 5 with a weight of 100. From 4 to 3 with a weight of 1. From 4 to 1 with a weight of 10, from 4 to 5 with a weight of 2, from 5 to 6 with a weight of 1, from 5 to 2 the weight of 2, and 6 to nowhere. All right, and implicit representation. So sometimes you don't need to store graphs. Sometimes some questions just allow you to calculate for neighbors of vertex, check adjacency, and determine all the edges without actually storing all the data and wasting valuable memory. If you can, you should try to use this method, as it's generally, it reduces the amount of memory used and the time for your code. All right. And comparison. So if n is the number of vertices and m is the number of edges, and d max is the number of maximum degree of a node, the following table summarizes between the differences between the representations. So in an edge list, space-wise, it uses 2m space complexity. Adjacency list, same thing. Adjacency matrix, it's n squared. Check for adjacency, it is m, since you have to loop through all the edges. For adjacency matrix, it's just 1, since all you have to do is okay, check out ij if they're adjacent. Adjacency list, it's d max, which is you have to loop through all the vertices that are adjacent to the adjacency list, that vertex. To list all of the adjacent vertices, for adjacent edge list, it's m. For adjacency matrix, it's n. Adjacency list is d max. To add an edge, it's all 1 for each. It's all constant for each of the values. And to delete an edge, for edge list it's M, adjacency matrix it's 2, since you have to, delete one value and another value. And for our adjacency list, it's 2D max. All right, and that gets to the end of our lesson. Does anyone have questions about what I've just taught so far?
Yeah. Do you mind like showing how to make an edge list like with like an actual picture of a graph?
Okay, so let's say we have uh, this edge list here, right? Let me get up idle. Okay, all you have to do is like, okay, let's say we get input for n, which is the number of vertices. So in input, then here we just m equals the number of edges here, right? And here, all we have to do is like create a list. So edges equals some edge, some list, some array, some list, I guess. And then we go for I in range m, and we just go x, y, meaning this is the value you start from, and be like, just get input for, so into I, for I in range, for I in input, split, and then just add edges that append x and y. All right. Do you want me to visualize this graph here?
Yeah, sure.
All right. So yeah, so this is how you just code up an edge list. Since all you have to do is just keep track of the edges. That's about it. So let me just go to whiteboard here. So here you have an edge from 4 to 3, an edge from 3 to 1, an edge from 2 to 5. So yeah, you can create 2 to 5. An edge from 6 to 1, and an edge from 3 to 6. This is how you kind of visualize it. And you just kind of just draw out the edges as you go. All right. Does that make sense?
Yeah, okay.
So yeah, all you just keep tracking is you're not keeping track of any of the vertices. You're just kind of keeping track of what edges exist on this graph. That's about it.
Okay. Um, so one last question, like, on the table, like, it also says V1 and V2. Like, what does that mean again?
So this just means which vertices are connected. So V1 is there's a there's an edge from 4 to 3. This edge goes from the vertex 4 to vertex 3.
Okay. All right.
And if you had another number here, that'd just be the weight of this edge.
Okay. Um, all right. So, I'm sorry, I'm just thinking about this. Like, uh, V1 and V2, that's just to say like they're two different vertices you're comparing, I
Well, no,
guess.
they can be the same vertex. If they're the same vertex, it just creates like a self loop.
Oh, okay.
So it's just which on this edge, what two vertices are connected, pretty much.
Um 4 and 3?
Yeah. So in this case, this edge here, 4 and 3 connected. This edge 1 and 3 are connected. This edge 2 and 5 are connected, and so on and so forth.
Okay.
Does that make sense?
Yeah. Like I I'm just so confused like why you would like have the V1 and V2. Why not just like completely ignore V1 and V2 and just list the edges?
Well, you have to keep
Like
track of what the edges are connected to.
hmm.
That was just the point of the V1 V2. It's just showing what edges are connected.
Okay. Oh, okay. Okay. All right.
All right. Does that make sense to
Okay.
everyone? Does anyone have any more questions? Going once. Let's see if anyone's typing in chat as well. So no one's typing in junior help. No one's typing in junior. Going once. Going twice. Going 3 times. All right, I guess that's it for today. Yeah, just there are no questions for assigning today. Overall, just try to grasp what graph theory is. Prepare for next week, since next week we'll be covering more about graph theory. All right. Have a good day, guys.